Okay, I think we're ready to go. My name is Jack Young, and I'm a research manager at CIRIA. Thank you for joining us for today's webinar about our new good practice guidance, buried pressure pipelines, designing for thrust restraint, or C816. Before we begin, I do need to just go over a few housekeeping points quickly. Today's webinar is being recorded. The presentations and recording will be made available at a later date. All attendees are in listen-only mode. Please raise your hand or send a chat message if you do have any problems with your connection or audio, and one of the CIRIA team will be there in the background to help you out. We do have a dedicated Q&A session after the presentations. However, during the sessions, please do put your questions into the Q&A box and state if you wish to direct your question to a particular speaker. We'll be keeping track of the questions as they come in, and one good way for you to interact with each other within the webinar is to click the thumbs up button on other questions. This really helps us to pick out the most popular ones if we've got quite a few to get through. Please also feel free to share resources with us in the chat as well. We are keen to hear about your experience today and would be grateful if you could complete the short poll as well at the end of the webinar. If you would like to receive CPD for this event, you will need to fill this poll in. Please also share your views and experience with us on LinkedIn, and make sure to tag us so we can repost where possible. We do hope to be finished up around 12:30, so it gives you plenty of time for lunch. So just quickly, with an overview of who we are for those that aren't fully aware that might be tuning into one of these webinars for the first time. We recently celebrated our 60th anniversary as a not-for-profit member-based organisation. So our core strength has always been improving performance through collaboration in the built environment and construction sectors. So we do this by delivering independent guidance, typically such as the SUDS manual, the ROC manual, International Levy Handbook, asbestos, biodiversity net gain guides, and many more. We organise around 50 events per year, mostly online at the moment, ranging from topical conferences to annual debates and lectures to webinars on our guidance, such as today's topic. We are a relatively small but growing organisation with around about 80 members, which you can see on the slide here. So it's great to see many of you here today, and just give you a second to take that in because there's quite a few members, and thank you for being our members, I suppose. I would also like to quickly say a huge thank you to the funders of this project. Your contribution has been invaluable for the production of this work. And another quick shout out to the lead authors of the guide at Stantec, Martin Long, Carl Vaughan, and Richard Hipkiss. One final thank you as well to the wider project steering group who have helped review the guidance throughout the various stages of development. It's been a long time in the making, and your contributions have been vital every step along the way. I won't go through every name, but it's great to see some of you in the audience today as well. The project team would also like to quickly thank Matthew Braid, Omar Shalebi, and Mayowa Sayinka, who have provided the support, additional support in the guide as well. So that's pretty much all from me from a CIRIA point of view. So with that, I'll hand you over now to our chair for today. So please welcome Philip Clisham, an independent consultant and the chairman of our project steering group. So over to you, Phil.
Thanks, Jack. Yes, I had the pleasure of chairing what was an excellent group of 24 people on the project steering group, who were, as far as I'm concerned, some of the leading people in this field in the country. So we had some great conversations. I think between us we produced what is an excellent guide. I'm kind of old enough to remember the original thrust box guide, the current one, C128, being published in 1994, and had an impact then and has been a key guide ever since. But the reality is that the pipeline systems that we use today have evolved and changed. We've got widespread adoption of continuously welded pipe systems, which sometimes need thrust blocks, but not always. And alongside that, there's been the development of tied spigot and socket systems, pipe systems, and Of course, the utility companies are being asked to minimise working time in highways and find ways of maintaining supplies to customers even when the mains are being worked on. So there's a whole series of under pressure fittings that have been developed, which sometimes need thrust restraint, often need thrust restraint. So this new guide, I think, is very important, and I think it reflects the industry that we work in today. And so I'm really pleased with it, and I'm pleased that it's actually been published at last. We've got 4 speakers today for you. There's Martin and Carl, who will provide an overview of the guide that's been published. Then Guy Cleveland and Jim Tresnan from Thames Water and United Utilities, respectively, will provide a perspective from the water company's point of view. And so, without further ado, I'll stop talking and I shall introduce Martin and Carl. So, Martin Long is head of Stantec's Pipe Technology Group and a very well-known technical specialist in this area. And so it was really good having Martin on board, and he worked very closely with Dr. Carl Vaughan throughout, who's one of Stantec's main geotechnical engineering specialists for the water sector. And they were also supported by Richard Hipkiss, but it's Martin and Carl who'll be giving us an overview today. Thank you.
Okay, thanks, Philip, for that introduction. So yeah, as Philip said, my name's Martin Long. I'm a pipeline engineer for Stantec. I've been working alongside Carl Vaughan, geotechnical engineer, and Richard Hipkiss, structural engineer, also from Stantec, plus the wider steering group on developing this new guidance, which we're going to run through today, give an overview of its contents. Okay, so in essence, up until recently, thrust block guidance has been written and still is in CIRIA Report 128. There is a few years ago a BS standard on restrained joints for ductile iron pipe that was published, and there's also the buried pipeline structural design guidance BS 9295. And also the IGN for calculating end loads on polyethylene pipe fittings. So what this new guide does, it sort of blends all of these in some aspects and brings new things in as well. So the CIRIA 128 has been updated, and we'll go through that in a bit more detail. The restrained joint has been aligned with the processes that take place in this new thrust block guide, along with the trenching detail that we get from the structural design. So they all talk to each other, they all fit, and then likewise the PE end load contraction is also aligned with the processes that have been developed into this new guide and the trenching details that you use in the UK. Okay, so in essence, there's been many new things that have been introduced, but the main, some of the main parts of how we've updated the thrust block part of the guidance is we've now split the reduction factors, or the factors involved with passive resistance and sliding resistance. So there's been an acknowledgement that sliding kicks in before passive, and so those factors have been split. We've also introduced some side sliding on the block. So there's been many other things, but in essence, they are a couple of the big ones that have been introduced. The restrained joint system, which is now within this guide, I mean, it's essentially the same as thrust block design. There's passive resistance, there's sliding resistance, and they both methods talk to each other now. They all draw upon the same geotechnical principles. Okay, and then likewise the contraction that you get at the end of a welded polyethylene pipe, or any kind of welded pipe, to be honest, that has now been included in the guidance to prevent joint pull-out for when these things are pressurized. And what's sort of new in this guide is that we've sort of taken account of the buried environment to reduce the contraction force. So depending on the length of your pipe will depend on which of these formulas you will need to implement. And sort of this section here is how you would normally calculate your contraction force due to internal pressure and to any temperature changes. But then we have this reduction factor, which sort of takes account of slight movements in the block in order to mobilize resistances, takes account of the friction around the pipe, the elastic modulus, the amount of material, etc., etc. So all of those then feed in to reduce this contraction force that you're designing to. Okay. So we'll now sort of move over to Carl, hand you over to Carl. We'll talk about sort of the geotechnical updates or geotechnical based updates that we've introduced into the guide, and I'll come back a little bit later to talk about some other things that we've put in.
Okay, thank you, Martin. Yeah, as Martin and Phil both said, I'm a geotechnical engineer at Stantec here, and I was mainly responsible for the wording of the geotechnical updates in the guidance. We've introduced 3 new thrust restraint design classes. There was previously classes there, but we'll look at those in more detail in a minute. We've updated the soil descriptions and classifications. They were fairly old. They're now in accordance with the latest BS 5930. We're now allowing a contribution from fill or engineered material, including the trench backfill, as a contribution factor to the ground resistance for thrust blocks. We've renamed the thrust reduction factors as displacement limitation factors, which is a little bit more descriptive. And as Martin mentioned before, we've now got separate displacement limitation factors for the passive resistance and for the sliding resistance on the base and the sides of a block. The sliding resistance contribution along the sides of a block is allowable now, but only for certain soils. I'll talk about that more in a minute. And we've also introduced a procedure for designing with groundwater level at any level. As you know, the previous guide permitted you to either consider the water below the block or at ground surface, particularly if you assumed it at ground surface. In drained granular soils, that could lead to quite some conservatism. Okay, if you could advance the slide, please, Martin.
All right, I'm trying. I seem to have lost the ability to advance slides.
Oh dear. Right. Okay.
Susan can help us there.
Is Susan there to help? Excellent. There we go.
It's gone through one.
Brilliant. Okay. Yeah. So we have 3 design classes. Class 1 is sort of routine designs. Class 2 is where you might require some specialist guidance, or you shouldn't design Class 2 designs without specialist guidance. And then Class 3 it is basically the guide doesn't cover this design. They're closely allied to the geotechnical categories that you would find in Eurocode 7. You can see the descriptions on the right hand side there. I won't reread those, but basically routine design can be taken by can be undertaken by any reasonably qualified or experienced civil engineer. We would still recommend that you get specialist geotechnical advice and involvement, but it can be done without that, and is suitable for thrust actions of less than 1,000 kilonewtons, generally looking at simple horizontally or vertically loaded thrust blocks or simple restraint joint systems. And also Class 1 design would be in a position where there isn't interaction with adjacent services, and within good ground conditions. So we're talking about firm and stiff clays, medium dense gravels, and some engineered fills. For class 2, we would recommend that specialist geotechnical guidance and pipeline systems guidance is used for the design of these. The class 2 designs can be applied to systems receiving higher thrust actions, and also for non-standard thrust block shapes, maybe those thrust blocks where the block is below the pipeline and there's an upstand to connect the block to the pipe, for example. Class 2 designs would be required in what we would call poor ground materials, so silts which can behave in a drained or undrained manner, very soft clays, or loose sands, or some engineered fills. And it would probably, class 2 designs would also cover where there are interactions with adjacent services or structures. Class 3 is basically anything else, as it is in Eurocode 7. We rule out coverage of the report for very poor materials, i.e. highly compressible like peat, or something organic or decaying or putrescible, or anything that might be, extremely soft or loose. And we also, the design just doesn't cover structures in highly seismic areas, or areas with persistent ground movements where it wouldn't be suitable to provide a thrust restraint. Okay, if we could advance to the next slide, please. In terms of soil descriptions, identification and classification, we strongly recommend in the guide that your soil or rock identification is undertaken by a trained, competent person, and supervised or undertaken by a geotechnical specialist. That way you get the most out of your design, because it means you don't have to introduce too much conservatism into your parameters. The description and classification is in accordance with the latest BS 5930. So you'll see the things that you're used to these days in terms of state of compaction, consistency, and strength descriptions. We've beefed up the Appendix A from the previous guide. It provides a bit more help now in identifying materials for lesser quality people. We recognise lesser qualified people. Sorry, we recognise that these days, where we want excavations open for the minimum amount of time, you might not be doing in advance ground investigation works, and therefore the only chance you get to confirm your ground conditions is by an inspection when the excavation is open. And so the field identification procedures are really aimed at helping with that and making the most out of what you can see. And we've also provided a small amount of guidance, key guidance for silts, which depending on the secondary constituents, if you had a fine clay silt, for example, it may well behave in an undrained manner, and you can treat its design as for a clay. However, if it was a sandy coarse silt, it would probably only behave in a drained manner, and you need to treat it completely differently for design. So we've covered that as well with some key guidance. What I believe is a very good thing in this guide, rather than essentially for a thrust block having an area of the block that provides no resistance because it's bearing against a trench fill. In the old guide, that trench fill wasn't allowed to be used as resistance. However, in the new guide, if you can describe and define that material in engineering terms, you are now allowed to use that to contribute to the resistance. It also removes this issue where we just can't do a thrust block there because it's made ground. If that made ground is in such a state as you can describe it, then you're allowed to use it in the resistance. There's still some materials though that we strongly advocate against not designing thrust restraints in, and they would be things that are classed as class 3 designs, basically out with the guide. The soft, organic, decomposing or decaying forms of made ground. Okay, if we can have a look at the next slide, please. Okay, so the displacement limitation factors, as we now call them, are replacing the thrust reduction factors. What we realized in looking at the old guide is that you could, on the face of it, look at it and say, why have they got those huge factors of safety? We must be over designing this. We're designing for a resistant ultimate thrust with some huge factors of safety, but actually those thrust reduction factors were there because it's actually a serviceability limit state design. We are resisting the thrust, but with a restricted movement. You could resist the ultimate thrust without any safety factors, but what would happen is that the block or the thrust restraint would move more than could be tolerated by a standard pipe joint, and that just wouldn't be suitable. It would still fail a serviceability condition. So the guide is designed to typically limit movements to between 5 and 10 mil, which can be accommodated by a standard pipe joint. This whole theory was defined very well in the previous guide, but the term that they used, thrust reduction factor, was not particularly self-explanatory. So in the new guide, we've called it a displacement limitation factor. And basically what it does, it takes your thrust force and produces a thrust block, which when its resistance is mobilized or the ground resistance is mobilized, the movement is limited to a suitable amount. And what we have done, we've recognized that the portion of the thrust that can be resisted is resisted with a lesser movement in friction than is resisted by the passive resistance, and therefore we've split the displacement limitation factors. There's a set that run between 1.5 and 5 as the previous guide for passive resistance, but where you're considering sliding resistance, be that base or side, the new range for the displacement limitation factors is now between 1 and 3. So we have offered some reduction in conservatism there in the design in the new guide. If we can go to the next slide, please. Okay, as mentioned, the side sliding resistance is now allowable. It's only where we have this is for thrust block, sorry, and this is where the sides of the thrust block are parallel to the direction of the resultant of the thrust, and they are limited to certain soils. When you cast the block, you might, if you cast it against the clay, for example, might be some shrinkage of the concrete or the clay because of the heat of hydration, and there may not actually be a bond there. Certainly not quickly, and in the time between when you cast the block sets and the first activation of the thrust force comes into action. So that therefore we've only considered sliding resistance for uncemented granular soils, which immediately you maybe remove trench supports, that they will apply themselves against the thrust block with a minimum of active pressure. And so what we're saying is you can allow some sliding resistance along the sides of a block in uncemented granular soils. It's a little reduction in conservatism over the older guide, and it is helpful. It's particularly helpful maybe where you're designing a block that only relies on sliding resistance. There are some situations where you may wish to have an open excavation in front of the block, and so you have no passive resistance. So you're designing with side and base friction only, and in that case, it would be helpful. Next slide, please. Okay, and I think we're Martin and I are really happy with this one. The previous guide mandated that you either design with groundwater level below the base of a thrust block, if you knew that was clearly the case and would be for the lifetime of the thrust block, or it said you must design with groundwater at ground surface, and particularly where you had granular drained materials, that created a huge reduction in the passive resistance that you could estimate, and therefore blocks were turning out really quite big with groundwater at ground surface. What we've done, we've introduced a buoyancy coefficient, which essentially looks at the depth of the water in relation to the base of the block, and the higher the water is, the bigger the contribution from the groundwater is, the greater the reduction in unit weight of soil that must be applied. Therefore, if you have a low water table somewhere within the block, you're therefore able to make savings in block size over the blocks that you would have designed using the previous guide. The procedure is not quite as good as if you design from first principles. That might get you just a little bit more resistance. However, is a quick and convenient way of estimating the resistance and allowing for the groundwater at any level. And I think you'll find this particularly useful when you're designing in sands and gravels. Okay, thank you. I think I'm going to hand back to Martin now. Is that right?
Yeah. Thanks, Carl. Just make sure that's it. Okay, we got that. Okay, thanks for that, Carl. Whistle stop tour of the geotechnical updates. So there are a number of other sort of procedures that have been introduced into this guide, and there's a list of them, and we'll touch on them each individually. So we have introduced overturning stability, and I'll talk about that a bit more in a minute. We have allowed to brace against decommissioned pipes, and have brought in a method for using that as thrust restraint where you can't necessarily use a restraint joint system or thrust block. We've looked at how you connect a new restraint joint system to an existing non-restrained pipeline, and provided an additional method for being able to do that, which will allow you to take account of the short shutdowns that we're often restricted by. We've introduced guidance on under pressure connections, which was touched upon earlier. We've expanded guidance on the use of keys, thrust block keys, how they can be used. We've also brought in, and this is a very important one, brought in a calculation for the minimum distance your thrust block needs to be from adjacent excavations or adjacent structures, that sort of thing. And then there's been some guidance written on the actual structural design, reinforcement concrete design of a thrust block. Okay, so overturning stability. So previously, the design guidance was all based on the action of thrust, so at pipe level being central within the block, and that sort of didn't really allow much scope for transferring the thrust forces down below the pipe, which is often required. Our pipes are often at levels where there's lots of other utilities, particularly in urban environments, and so you might want to go down deeper to anchor your restraint. So this new procedure allows you to do that. You can effectively bring the thrust restraint down below the pipe level where you may have other services. Avoid all of that and design in that way. So in order to do that, we've obviously got some eccentric loading on the block. So we've introduced this this situation where we check the overturning, a very simple overturning procedure, and the most efficient type of thrust block that you'll get is one that's buried. So we may need to try and adapt construction practices to make sure we can bury where we can, and all of the weight of the backfill over the top can also be used for this resistance to overturning. Okay. Using a decommissioned pipe, sometimes we need to cap off. Very congested, very tight. We've certainly seen it done before, examples of it where the end cap is braced against the abandoned pipe. So what we've done now is we've formalised that into a method that can be used, and that involves grouting up the pipe that you've abandoned, so it can the grout or the concrete can interact with the pipe material, and then we calculate the length that you need in order to provide that restraint, and then you bear against that. So that's just giving another option in the armory to deal with thrust forces on pipelines. We've looked at when you construct a brand new pipeline offline, often using restrained joint systems, and then inevitably, you do that whilst the existing pipe remains live. At some point, you're going to have to connect in. That will mean using a bend to connect into. So, and that's often very challenging, because to get a thrust block behind this bend when this pipe needs to go back into service within a few hours, it can be very, very difficult. So what we introduced is a way of designing an inline thrust block. So you only need a short shutdown to chop out a piece of pipe, introduce a thrust flange, piece the pipe back up, put it back together. You've only got a short shutdown to piece this in, and then we've got the design procedure for that inline thrust block. And as you can see there, it's below the existing pipe, so you're not bearing on the new pipe that you've just put in the ground. So and it follows the general theory that your thrust force is coming this way from a bend, and it collides with a thrust force coming that way from a bend. So the restrained joint deals with this side of it, and then the thrust block will deal with that side. If the pipe can't move that direction and it can't move in that direction, then nothing's moving. So this is a slightly new procedure that's been introduced to allow for that situation. Okay, and then restraint of under pressure connections. So they could be line stops, they could be under pressure valves, they could be under pressure T connections. Now all of these situations will generate a thrust force within the pipe, and so when you think back to, I mean, some will be in line in an existing system, some will be teeing into an existing system. If you're using a restrained joint system, there's a realization that you can still get some stretch in this system as the restraint mechanisms link and connect. So if you were using a completely unrestrained system to tee in with, you would design a thrust block in the normal way using the T procedure. However, if you're using a restrained joint system, what we do is we just say we need to provide some support around the back of this to sort of encourage any flex or stretch in the system to follow the line of the restrained joints, rather than overstressing the pipe that we're connecting to. Similarly, for an inline restraint, under pressure valve, under pressure line stop, we need to bear in mind that with thrust blocks and thrust restraint, what we're trying to do is limit movement to very small amounts. And even if you've got an inline spigot socket system, that force is going to generate, it's going to compress these joints, that could overstress the end of the joint, It could cause leakage at the back of the joint, and leakage is ultimately what we're trying to avoid, because leakage can wash out surrounding ground and then things can exacerbate and the failures could develop over time. So we're basically introduced the methods for you to design thrust blocks for these under pressure systems. Okay. And then some additional guidance on thrust block keys, just to help with that. The key should be in proportion to the block, and the guide is limiting these keys to sort of 1/3 length and 1/3 height. If you want to go beyond that, then that's not within the guide, and you need to determine for yourself whether it's appropriate and the block will remain stable. Okay. And then I'll hand back to Carl on this one. This is the one that I think a lot of people have been really quite pleased about. If we design a thrust block and we need to excavate downstream of it, how close can we get to it? How far away do we need to be? You're on mute, Carl.
Sorry about that. I won't say too much on this, because otherwise I'll steal Jim Treson's thunder in his presentation. But basically, it simply works on the block relies on passive resistance to the ground. We have a passive wedge in front of the block, and there's an active wedge associated with a downstream excavation, and we just don't want the passive and active wedges to overlap. So we work out the minimum distance based on the size of those wedges, and providing your excavation is further away than the minimum distance, then you're good to go. The same can be applied to blocks on adjacent pipelines. If the thrust forces are acting in the same direction, then you'll have a passive wedge and an active wedge on the second block. If you've got blocks in with forces in opposing directions, say where you get to a T-junction, you've got bends going in opposite ways, you might have two passive wedges. So there's a procedure for that as well, depending on the direction of the thrust. And we have similar for restraint joints. When it comes to the restraint joints, it's a notional exclusion zone that we provide guidance on. The general suggestion is, if you've got neighbouring utilities that are outside of the zone, they probably won't be affected. However, depending on the criticality of those adjacent structures or services, we would say it doesn't rule out doing a check, a damage risk assessment. You should still do that. And the zone doesn't necessarily mean that you're safe to construct your restraint joints there, because you've still got to remember that the neighbouring utilities might have to be maintained, repaired at some point, and it's not just the services you need to consider, it's also the excavation, future excavations down to those. Do they also impinge on the exclusion zone? But we believe it's quite good guidance. It should be useful, particularly with things where you are making things like line stop, downstream connections, things like that. Okay, I'm going to hand back to Martin very quickly.
Okay, thank you. So just finally, just to cover off some small points about the structural design. We often see concrete reinforcement put in, designed to sort of Euro codes, which are related to buildings and bridges and things. So it basically sort of puts some words in to say, well, that's not necessarily required for crack width, and really to only put sufficient reinforcement in that is required for the stability and the longevity of the block. And that might be, and you might only need that for sort of upstands, keys, under pressure connections, and things like that. And also for the structural engineer to understand, how the loads, the pipeline or the design engineer have generated those, because sometimes they would already have factored the loads. So the structural engineer needs to understand how they've been calculated, so as to not double factor to try and reduce that reinforcement. Okay, and low carbon concrete and fast cure concrete has also been discussed. And that brings us to the end of explaining the updates. And we'll hand over back to our chair, Phil. Thanks very much.
Thanks, Martin. Thanks, Carl. Time pretty well there, so that's excellent. So that's an overview. Hopefully there will be some questions from that. We've already got a couple. I'd encourage people, now's your opportunity. You've got the authors here ahead of you. So if there are any questions, put them in the Q&A. And in the meantime, we're now going to hear from Guy Cleveland. Now, Guy is the industry quadrant lead for Thames Water, which basically means he's technically responsible for the infrastructure program. So we're really pleased he's been able to find the time for us today and give us some time to provide a perspective, or Thames Water's perspective on this. So Guy, I'll hand over to you. Thank you.
Thank you, Phil. Thanks for inviting me to come and speak for a few minutes. I don't want to get a Phil Clisham watch tap, so I'll whip through my slides as quickly as I can. And thank you to Martin and Carl for stealing a lot of my thunder in the previous slides. I'm going to talk through, I guess, thrust in Thames Water, but also and the lag is back. There we go. But also, thrust in Thames Water, and then give a perspective on what I think the benefits of CIRIA 816, and apologies if I refer to it as 1120 at any point. That's kind of what we called it in the working group. So thrust in Thames Water. I went to our capital delivery team and I said, I've got this presentation to give. Is there any chance you could send me a couple of photos of congested excavations where I can talk about some of the challenges we see with constructing thrust blocks, particularly in London? And I'm now the proud owner of 6 terabytes of trial hole photos. But as you can see, we have a lot of utility congestion. It's probably not different to most major urban centres for other clients. Just London happens to be pretty big. So once I'd asked that question of capital delivery, I tried to get a bit of a handle on how many thrust blocks they thought we might construct this AMP. And answers ranged from what's a thrust block to thrust blocks, way too bloody many. So I don't know how many, but to give an idea of kind of our infrastructure program, certainly the big hitters in AMP8, we've got 585 kilometers of distribution main replacement, approximately 35 kilometers of trunk main replacement, and 80 kilometers, although that could stretch to maybe 100 kilometers of rising main replacement. We're going to be building a lot of thrust blocks. Within Thames Water, and I would say the wider industry, in my experience, thrust blocks are often misunderstood. In my role in Thames Water, I see more than my fair share of ill-conceived thrust block designs. I see some really great stuff as well. I'm a nerd, I'm not afraid to admit it. I love seeing a good thrust block design. If I speak to particularly our contractors, but not exclusively our contractors, thrust blocks are often seen as unnecessary, expensive, impossible to fit in, and sometimes they are. And I think CIRIA 816 is going to help to address some of the issues that we see. So like I said, kind of Martin and Carl have done a great job of introducing some of the changes, and I'm just going to give a bit more Thames flavour to that. So one of the things that I have got involved in is looking after our asset standards, but also reviewing waivers against the asset standards. So one of the things that is currently in our general civil standard is that thrust blocks that aren't designed in accordance with CIRIA 128 must have a factor of safety of 3 against overturning without making use of the overburden. And as you can see, 2/3 of the waivers that we see are in relation to that. Because of the congestion, we often end up designing the thrust blocks that Martin spoke about with what can be quite significant overturning moments applied to them. So what we have approved, so waivers previously have been approved for reduced factors of safety ranging from down as low as 1.1 without the use of overburden up to maybe 2, maybe 2.5 with, but kind of we are routinely up against this and have to account for it. So the introduction of a standardized approach to overturning means that I can very likely remove this clause from our civils specification. It should give rise to a reduction in thrust block size across the patch, but also critically for us with such a big program, allow us to deliver at more pace. So having not having to wait for waivers to be approved prior to going into construction, that kind of thing is going to be really useful for our design, for our contractors. So Carl mentioned in his presentation about using the sides of thrust blocks to provide sliding resistance, and actually, I don't want to say they were ahead of their time, but Stantec back in, I think, about 2012, I have a feeling it was in the run up to the Olympics, got involved in a project. This is the example on screen is Notting Hill Gate. It was right outside of Notting Hill Gate tube station. Again, extremely congested, massive pressure from TfL, because it's in Notting Hill Gate. It was shortly before the Notting Hill Carnival as well. So we had everything going on here, massive congestion, but also the tube station, tube tunnels. We couldn't put a piled thrust block solution in here, so we really had to find something else. With the space available following CIRIA 128 strictly, our achievable thrust reduction factor was less than 1. But luckily a very clever engineer suggested, how about we make use of the resistance at the sides, and that allowed us to get a thrust reduction factor of more than 1. But I don't think much more than 1. But equally, this thrust block is still in service today. No known issues. So it does work, and here really got us out of a tight spot. So something that we see a lot of pain from within Thames Water it relates to polyethylene pipes, but I guess continuously welded pipeline systems and the loads that they can generate in response to pressurization, but also changes in temperature. Now, the eagle-eyed among you will notice that an anchor block here wouldn't have saved us, but it was the best example that I could find of photos displaying the impact that this contraction can have. So I think the wider industry has been picking up that this is an issue, and certainly in conversations I have with other water company employees, people are starting to see this as an issue. Thames, we do see failures, not regularly, mercifully, but we do see failures. I think, in my experience, these are often misunderstood, and the cause of failure is often misattributed. Here, we're fairly confident that the flange adapter wasn't torqued up correctly, but this connection between the two pipes, it could have been an unrestrained system, for example, that we were connecting onto, and instead of the failure happening here, it could have happened within, let's say, the cast iron system, and but that failure would have been misunderstood, misattributed. So Martin introduced this, and it's actually something that, in conjunction with Stantec, we've already implemented. I want to say twice, but it may actually be more than that, and it's been particularly useful for us in the AMP7 trunk mains program, where we were abandoning a number of trunk mains or lengths of trunk mains and making connections into new trunk mains. Where we just did not have space to construct a traditional thrust block, or couldn't make use of a piled solution, for example. So at least 2, probably more, and I don't think it'll be the last we see of it this AMP. Now that it's so it would have been included in those waiver stats that I showed earlier. I'm not sure which one, but these kind of non-conventional thrust restraint approaches, we're just having to use now because we don't have space for anything else. So this for us, the introduction of the restrained length as an approach under CIRIA, I think for Thames Water, is going to be massively beneficial in our mains rehab program. As I said before, we're doing 585 kilometers of mains replacement this AMP. In lots of instances, we are installing new valves, bends, etc. Lots of polyethylene, but certainly in conversation I've had with some of our contracting partners, they're open to the use of using some restrained pipe systems in place of thrust blocks. Also potentially using thrust blocks in concert with restrained pipe systems to reduce the overall kind of burden on thrust. I know that there was a British standard introduced, I think it was in 2021. I would say uptake of that has been relatively slow. Certainly we're not seeing it being widely adopted or widely used by our contractors. But its inclusion in 128, it will mean that it becomes a standard approach for Thames, and I think is going to bring significant benefits, particularly to the mains replacement program, but also across the estate. And I've got to the end in about the time that I said I was going to take without getting a watch tap from Phil, so I'm very happy with that.
You've dragged some time back. Well done, Guy. That's brilliant. Thank you very much. Excellent, and thanks for the questions that have been coming through. Keep them coming, and we'll see how many we can get to. So we're going to move on now to Jim Tresnan. So I'll introduce Jim. Jim's got what is at times a very challenging job at United Utilities. So he gets to deal with the major issues, the really difficult repairs that often decisions have to be made under great pressure and without all the time in the world to do geotechnical assessments and the like. So Jim has to deal with stuff on the fly. So really interested Jim's perspective on this. So I'll hand over to Jim Tresnan. Thank you.
Thanks, Phil. You build me up to sound like I'm Red Alert, the way I must rustle into these issues. But you're quite right. When we do have issues on large diameter pipelines, I seem to be the one who gets the call from the director asking me to go and have a look and see what the issue is and how we can best deal with it. So this is why when the suggestion that we could update the CIRIA 128 document and bring it up to date with modern practice and techniques and everything, I was very interested in it. And believe it or not, that was about 5.5 years ago when we first started talking about it. So yeah, I was only 16 then. So what did the original CIRIA document say? What did 128 say? And this is all in relation to excavations adjacent to thrust blocks, and it recognised that when you undertook such work, it could have potential consequences. It said consider the effects of any adjacent services or situations may lead to subsequent excavation near to your thrust block, and so may undermine the capacity of the block. And then elsewhere it said, should a second pipeline be laid alongside a first in a common adjacent trench after the first has been commissioned as in operation, careful consideration must be given to the security of the first pipeline if it is in service while ground is opened for the second time. So it understood that this was an issue. It recognized it, but it didn't give us any mechanism for sort of assessing what the potential consequences of it would be, and how we define how close we can work to existing thrust blocks without potentially undermining them. So our new document, which I'm glad Guy was also struggling with the reference for, because I'm still coming to terms with it, but the new C816 document starts to address this, or more than starts, it gives us a really good way of addressing this. And Carl touched on this earlier, that I was going to theme on this subject, and I've just sort of tried to clarify what's written in the document, but with this image where it articulates clearly where the passive and the active zones are in relation to the thrust block on the left-hand side and the excavation on the right-hand side. And it says, to ensure the passive resistance on an existing thrust block is not compromised, the passive wedge of soil acting against the bearing face of the block and the active wedge generated by the downstream excavation should not be allowed to overlap. So we're trying to avoid those two triangles coinciding, and if that situation occurs, then we've got a potential failure to occur. So what I wanted to do was touch on an incident which we had in United Utilities, and I'll just sort of hopefully tee up the description by describing the system that it happened on. So this is a drawing of an aqueduct, part of an aqueduct system that we have. The three lines of pipes, 2 cast iron, 1 steel, not welded steel as you may assume, but steel with lead run joints, so a push fit type of socketed arrangement, and obviously what we're looking at here is a what we describe as a crossover arrangement. So if we have a burst or we need to take a section of one of the mains out of service, we then have the facility to cross feed flows from one pipeline to the adjacent pipelines over that section which is isolated, and it obviously helps to maintain the capacity of the system and allows us to to keep the supplies going as well as we can. So here in this image here, we've got running off to the sort of the top side of the image, we've got some scour pipe work which is draining, can drain the pipe work, and at either end we have these what are commonly described as buzz bars, which are the crossover arrangement, and in between are the valves that would isolate the system. So that is the general purpose of this piece of pipe work. And so the example that I wanted to give was when we tried to do some work on an upstream section of the pipe work on the centre line, on line 1, the cast iron pipe. And the activity that we were undertaking was in order to enhance the life of the pipe and improve water quality. We were undertaking a slip lining program of the pipes. I should say that these pipes are all approximately 40 inches in diameter, a metre if you're not into old money. And so essentially, we were putting in a large diameter pipe, 900 diameter PE welded pipe that would be slip lined into the existing hose pipe. And as part of that work, we undertook an excavation for a reception pit for the slip lining, sort of immediately downstream of one of the crossovers, behind a section where there was a thrust block, obviously aligned over the top of the existing main. So that was the work that we were undertaking, and what happened is we identified after the event that we had a burst event that occurred. And we identified after that the cause of the burst was the proximity of the excavation for the reception pit on line 1. It wasn't immediately apparent because it wasn't just line 1 that failed, but line 2 also failed during the incident occurred. But it didn't happen immediately. We had the excavation undertaken, and it was open for several weeks before the full incident unveiled, and we had a major burst event occur. So, you know, there was presumably some initial ground disturbance, but it took a while to materialize, and, you know, the disturbance occurred later. Sorry, the initial ground disturbance probably commenced a lot earlier than we understood, because of that we hadn't seen it until the failure occurred. So, so this is a sequence trying to explain how the incident unraveled. So it's going to skip through into stage 2 now, where we've got the excavation has been undertaken. It's compromising the passive soil resistance to line 1. Lines 2 and 3 are starting to move, and we've got a leak occurring at line 1 from the bottom edge of the existing socketed joint. And that is then into a high pressure leak, which starts to wash out the material surrounding the thrust blocks, and we lose the passive resistance. Line 2 thrust block is then unable to restrain the thrust force, and the rapid movement of line 2 thrust blocks causes the joint failure on line 2, and then simultaneously line 1 is pulled out as well. The passive soil resistance around line 1 thrust block no longer exists. The thrust block moves, causing the line 1 to fail, and line 2 thrust block momentum continues in unison with line 1. And then ultimately we have a significant pressure drop, and the thrust blocks come to rest, and the soil washes out a wider area, but line 3 doesn't move. The line 3 joint stayed intact, and that pipe didn't actually fail. So that is the sort of at-rest position, and this is what it ultimately looked like. So what you can see here is, obviously we've got the 2 open joints on the left-hand side of the screen, adjacent to the brickwork. Line 1 being the center pipe. This picture is taken from pretty much on line 3, and line 1 and line 2 are both moved. Being opened up, you can see the distance between the thrust block and the excavation. I think that the thing that isn't probably initially apparent, and I probably need to reinforce it, is that obviously when this was occurring, you know, there was no, these pipes weren't exposed. They were fully backfilled, and the ground level was at the top of the brickwork that you can see on the right-hand side. So, you know, we've lost an enormous amount of ground from around the pipes. It's quite sandy material. Flick on, we can now look from the opposite side, and you can see sort of some of the displacement and movement of the joints. But again, it sort of hopefully reinforces the amount of material that was washed out, and the proximity of the excavation on the downstream side. And, you know, the purpose of sort of sharing these slides with you is to hopefully demonstrate the, you know, the impact of an event such as this. Many years ago, one of my predecessors was called out by the police, and it wasn't in relation to a thrust block, but one of the aqueduct pipes had burst, and the police believed that it was some sort of terrorist action because of the crater that had been formed by the washout, and the, you know, the volume and the pressure of water that was coming out of the pipe as a consequence of the failure. So you know, this is quite dramatic when you see it in the flesh. So in there we go. Sorry, too laggy. So yeah, in summary, then, as I said, the issues of excavations adjacent to thrust blocks isn't a new one. It's, you know, been understood. It was understood in CIRIA 128, but they hadn't gone so far as being able to identify a method for assessing when this was an issue. The new guide, this C816, defines a method of ensuring the passive resistance of an existing thrust block is not compromised. It introduces a displacement limitation factor, which Martin and Carl described before, this DF value, which is used to limit movement to very small amounts, thus preventing leakage at joints. And, you know, this is what we've seen here. We've seen a jet that initially occurred due to a small amount of movement, and then that has removed the fill material from around the pipe and caused the greater event to occur and the sudden failure of the pipe. So yeah, I just wanted to emphasize that, you know, when we've failed to identify this as a potential issue, relatively small movements in pipe can cause, you know, leakage, and that can then set off a chain reaction, which, yeah, should be avoided and is quite dramatic. So that was my piece. Thank you for listening.
Thanks, Jim. That's brilliant, and illustrates what happens when we get things wrong. So if I could ask all the speakers now to turn the cameras and their microphones back on, we'll go into the question and answer session, where you'll be pleased to know that we've got some excellent questions. So we'll test you. I'm going to follow the thumbs up, and that start with the one that's got most thumbs up. Now, I apologise if I pronounce surnames wrong. I'll do my best, but some excellent questions coming from Maria Teixeira. So the one with 5 thumbs up. When connecting to an existing main during a short shutdown, it was mentioned to connect back to existing. Is it acceptable to allow main to pressurise before upstand cures? Also, is there any reference in the guide on the use of rapid set concrete in thrust blocks? So I think this is one for Martin and Carl, really. Do you want to take the lead on this, Martin?
Yeah, sure. I was. So no, absolutely not. We can't allow the thrust block to be loaded before the concrete has cured and reached appropriate strength. So what we sort of mentioned earlier was the ability to have a short shutdown that allows you to piece a bit of pipe in, which with a thrust flange on it, and then it reinstates the pipe as if nothing had happened. So you can turn the main back on without introducing any thrust forces whatsoever. But what you've been able to do is put that thrust flange in the system, and then that allows you to cast your concrete around it, give it time to cure, reach strength, and then once that's done, then you can connect your pipe to it. So no, we can't load a thrust block before it's cured and reach strength. So
I often find it's good to put sequencing drawings in, so people can sequence and understand the order in which you've envisaged it. The second part was the use of rapid set concrete.
Right, yeah. So that is touched upon in the guide, but I think they are they're not standardized. So each rapid set concrete will be there. You know, each individual supplier will have their own formulas for that. So you would need to speak to them on an individual basis. But it's certainly talked about within the structural element of the guide. Yeah.
Anyone else would like to add to that? Go on, Carl.
Yeah, I was just thinking that yes, the rapid set concrete mixtures are all different. They have different heats of hydration, which can have an effect on the pipe that it's surrounding, and so you do have to be careful. But as Martin says, there is an amount of guidance there to do with being able to decrease your cure time to be able to bring thrust blocks back into service quicker.
All right, thank you. Next question that we'll pick on was from Daniel Bond and Samuel Williams, and it's about the thrust reduction factor. So with the thrust reduction factors being based on serviceability and minimizing movement for pipe joints, is there any guidance on using smaller reduction factors for welded systems? Now, there's a little bit of confusion there, but it could be where I'm reading the question. Samuel Williams says, offer pipe systems where you could tolerate more than 10 millimeters displacement. So my understanding is if you're tying a welded system into a spigot and socket system, It's the amount of movement the spigot socket system could tolerate. And that would be the limiting factor, because the welded system is welded, so it shouldn't be a problem. But if you've got joints that can tolerate much more than 10 millimeters of displacement, how does the guide allow us to reduce that thrust reduction factor?
Yeah, can I have a go at this one, Phil?
Yes, please do, Carl. Yes.
Yeah. So in producing the guide, we did rather a large literature search on the potential movements of buried structures in mobilizing the passive resistance and frictional resistance of the ground. But we were limited to a literature search. And what we found is, just as a general rule, is passive resistance mobilizes with a much greater movement than frictional. But we couldn't really do a great job of reducing the displacement limitation factors above those that were in the previous guide. They'd done a pretty good and thorough job. We provided some reduction in conservatism, but not a lot. But what I would say is, if anyone would like to make a big donation to CIRIA, to be able to, some students to go into a lab and actually do some full scale tests of applying thrust forces to blocks and measuring the movements for some later iteration of this guide, there may well be opportunity to bring those thrust reduction factors down or rationalize them some way. The other thing I would say is, although we don't give specific guidance in the guide where there are maybe adjacent fittings to a thrust block that can tolerate more than 5 to 10 millimeters displacement, we do say that, and you would have to do this under the guidance of a specialist, and it's essentially out with the guide, but it does recommend that if you want to do your own study to determine what resistance you're going to get for a given movement, you could do that. Whether you do that with a physical model or whether you do that with like a finite element model may not matter so much, but you'd have to do it under the guidance of a geotechnical specialist. But you could investigate those those displacement limitation factors for yourself. But there's only really sort of indicative guidance in the guide. There isn't any specific guidance for increased joint displacement capacity and equivalent reduction in displacement limitation factor.
In summary, we think there is potential, but we couldn't put numbers against it. So we would like to do some more research in that area if we could, for a later iteration. I think that's a fair assessment. Yes.
Yeah.
Another question from Rubel Ali. How often, if at all, are steel piles used as thrust restraints, and how effective are they compared to concrete thrust blocks? What are the general technicalities around steel pile restraints? If you want to take this, Martin, or it's another one for yourself, Carl.
Yeah. We don't particularly put any guidance in there other than to say if you can't fit in a design that's mandated within the guide, that you might consider one of those under the supervision of a geotechnical specialist. They are, of course, possible, but because there's a complicated interaction between the pile and its movement and the ground in resisting the force, you're probably talking about finite element modeling to confirm the serviceability state criteria that you need to meet. The ultimate limit state criteria, i.e. will the pile resist the thrust load trying to bend it? You can probably do that quite simply, but the serviceability limit state would be a case of modeling, I think. And so we don't provide guidance on that in the in the guide, but we do say refer to your geotechnical specialist and see what they can do for you.
So again, it falls into this category where they are often used where you've got limited options, but it becomes a specialist area, and there's no specific guidance, as Carl says, in this particular guide. Anyone else like to add to that?
I mean, sorry, Martin, do you want to go first?
Okay, I'll just say, yeah, we don't provide the guidance for designing it, but you know, the limits that you need to design for, the 5 to 10 millimeter movement are in the guide, so they would carry through as well, unless you had joints that could tolerate, you know, greater movements, basically.
Okay, go on, Guy.
I was just going to add, so we do within the Thames estate have some steel pile thrust blocks, not very many. I'm not by any stretch an expert, but they look to be less efficient overall than kind of concrete piled or traditional thrust blocks, but they're often used where we need a very quick solution. Can't have remain out of service for any length of time. So can be used in that context, because obviously there's no curing or anything else to go with it, and have become permanent structures within our estate, but the exception rather than the rule.
Yeah, I would agree with that. Okay. Again, there's quite a few questions coming on the whole sheet pile thing, so it's perhaps one for a future edition that we need to consider. Right. Let's have a look. Choose another one. You Thomas Nichols, you earlier showed an example of a redundant pipe being used for restraint for a capped pipe. You mentioned the pipe being filled with concrete. Are there any issues with the type of joints in the existing pipe? Does the restraint rely on the soil friction of the redundant pipe or the compression resistance from the concrete, or both? Do you want to grab this, Martin? On?
Yeah, sure. Thank you. Yeah, you did right. It relies on both. So the idea is that the existing pipe will have the friction, it will remain buried and has the friction around it, and then the grout or the concrete is poured in to reinforce that pipe material. So you're then bearing against that. You're bearing against a grouted up pipe material which is surrounded in soil. So we feel that the risk of buckling that pipe is extremely low. You've got often a metallic pipe that your concrete is interacting with. It might be cast iron, ductile steel. It may be a plastic pipe or GRP, but the grout will reinforce that, and then the surrounding soil reinforces that as well. So we believe, on the balance of risk, that it's a robust solution, and the risks of buckling that pipe are low, you know. And it's often used when you're sort of got no other options. You know, it's trying to give the design engineer another tool in their armory to deal with thrust restraint. So yeah.
Yeah. The other purpose of the grout is it will prevent closure of setting gaps in the nearest joints in the pipe that's to be abandoned. If those setting gaps were to close up, your thrust restraint would essentially be reducing in length and allowing movement. So the concrete fill also prevents that.
Yeah, excellent. Okay, we've got time for just a couple more questions. Barry Granger asked, is there recognition of the reduction in friction on pipe lengths required to restrain anchored fittings caused by PE sleeving? So this is I mean, it's not something we often use these days, but there are different coatings for different types of ductile iron, for example, and steel pipes. Does the guide take account of the effect of different coatings?
Yeah, it does. It's reasonably basic in so much as you calculate the friction around the circumference of the pipe in the normal way, or the adhesion, and then there's a reduction factor applied. So if you've got a normal ductile iron steel coated pipe, for example, you don't reduce it. If you're in a polyethylene pipe or that sort of thing, it is a reduction factor of 0.85, and then if you've got a loose or extruded coating on your pipe, then that reduction factor is at 0.7. So that's how that's accounted for.
Excellent. Another one from Maria Teixeira. It was mentioned thrust blocks between PE mains and unrestrained pipelines, which is an important one for me. When using new restrained pipeline, can these just be connected to PE mains if pulling forces are within the limit of the anchor gaskets, for example? This is a ductile iron anchor gasket mains connecting onto PE mains, and is that ever a problem?
So, in my view, that's perfectly acceptable. The guidance is to prevent dislocation at joints, and if your system is installed correctly, a fully restrained system and a fully welded system, the joints can't separate. So, yeah.
I think, if I might add to that, I think that's generally correct. I think when you're pushing things up towards the limits and often test pressures on the PE pipe system, you've got to bear in mind the ductile iron anchored system is designed for normal thrusts that you'd see in a fully ductile iron system. So if you push it up towards the limits, you can often exceed what the anchor system was meant to take in the first place, and you crush a spigot end basically. And I've seen that happen. So you've got to be ever so careful with the polyethylene test. It's not often an operational one, and it's a massive negotiating down a different test pressure if that's the case. So you do have to be a little bit careful. But under normal circumstances, it would be okay. But in the extremes, you can push the anchor gaskets too far. Okay. And how are we doing for time? 12:21. We've got time for another question or two. So, in situations where excavation near an existing thrust block approaches or exceeds allowable limits, so this is an existing thrust block, so might be one for you, Jim, and there are no clear options presented, does CIRIA guide recommend any backup methods or mitigation strategies to ensure system integrity? For example, are there any temporary or permanent restraint alternatives described that can be used in such constrained conditions? This is second comers working near thrust blocks. Do you want to say that, Jim, or have any thoughts on it?
Not sure. I've got very much to sort of answer that one with, really, Phil. Yeah, I mean, if you're going to be working that close that you're falling outside of the realms of this guide, then I think the first option should be looking for alternatives. But I'm not sure that's answering the question that's being asked, really.
No, my own thoughts on it is you've got to, and there's always an engineer solution. This is why all engineers should understand how thrusting pipes are restrained, because if you're going to be working near them, you need to understand how close you can get before it becomes a problem. There are often ways, and we have to do this on awkward tie-ins sometimes, but it's first principle engineering, and yes, the guidance will give you the tools to calculate the loads, and then you've got to decide how are you going to deal with them. If you're going to remove the soil, then you've got to replace it with something else that will be an equivalent, would be my advice on that. But it's the sort of thing that comes up from quite regularly, and it's good that we can get hold of it earlier, sooner rather than later, and then you can think through how it can be managed. Does anyone else have anything to add to that?
I just did have a thought. Yeah, we're in a day and age where most utility owners have good-ish, reliable BIM systems and recording GIS systems, and it's vitally important that you record the location of your thrust restraints, be they blocks, be they lengths of restrained pipes, be they lengths of redundant pipes used, so that anyone coming along, any second users or whatever we called them, are made very aware that that thing is there. But to reiterate, if there's no alternative but to work within the zone, you've got to fully design, as you said, to replace what you take out. If you take the ground out, you've got to have a fully braced, immovable something to be able to create that excavation within the zone, and you've also got to remove that excavation support in a way that you don't compromise the passive resistance as well, if it was a thrust block, for example. So.
Quite a good question again for yourself, Carl, is from John Oxtoby. If undisturbed ground is not available, is compacted fill acceptable or capable of resisting thrust forces?
Yes, I would say it is. Yeah, but you have to compact a sufficient area with the replacement fill, such that that fill encompasses the whole of the passive zone. So you could actually use the downstream excavation calculation process to work out the size of the passive zone, and providing your area of fill is bigger than the passive zone, for example, then yes, you could use filled material to replace something that was there that was unsuitable. You can do that, yeah.
Excellent. Well, there are other questions, but I think we've got to watch the time, and I don't want to keep people later than we really need to. But thank you for all your questions. If there are any additional questions, please keep them coming in, and if there's any burning ones, CIRIA will pass them on, and we'll try and get answers to you. So, well, thank you for everybody. It's for me to really provide some closing remarks and close the session now. There's a new guide. We're quite proud of it. There's a lot of additional guidance in there, and we believe it reflects the industry today, but it doesn't cover every circumstance. It provides additional guidance, additional understanding. It is a document you can read, and you'll benefit a lot from reading through it. I've certainly benefited from working with the people and putting it together, and so strongly recommend it. And there's a room for improvements always. We would certainly welcome any comments and thoughts on it and on its use over the next couple of years. And we'd dearly love to do some additional research and improve it further if we got a chance in the future. But we believe it's a good step forward. So the speakers' presentations will be available, and will be there'll be a link circulated to those speaker presentations. We'll endeavour to respond to any questions, as you say, that have not been covered today. So just contact the CIRIA team, and those will work through. Now, there's going to be a feedback poll done. So we're keen to hear about your webinar experience, and we'd be very grateful if you could complete this short poll. And that should be on your screen shortly if it's not there now. So let us know and fill that in. That would be great. I'm also duty bound to talk to you about the delegate offer. So the report's now published. There is until the 9th of July an offer on where you can get it for a 20% discount. So it's £48 to CIRIA members, and I think it's 96 to non-members. So I say the instructions are there on the screen, and feel free to make use of that. So I'd just like to thank everybody that's had an input to it, and thank you all for coming along. And we'll close the session. Thank you.
Thank you.
Cheers.